Hello all, I hope you all are able to follow along with the material I have been teaching. Welcome to video 4. Today we will be discussing the cardinality of a set. So let's get started. Let's start with the definition of cardinality. The number of elements in a set is known as the cardinality of the set. It is denoted as n, and then we write the name of the set, sometimes with the pound symbol and then the name of the set, or sometimes with the first 4 letters of the word cardinality and then the name of the set. Sets are classified based on the number of their elements into 2 categories, finite and infinite. Infinite sets are further subdivided into 2 types. Let's look at the definition of finite set first. A finite set is a set with a fixed non-infinite number of elements. For instance, if you have a set X with elements A, B, and C, then the cardinality of X is equals to 3. And since we have the cardinality as a fixed number, we will call X as a finite set. Another type, which is infinite set, is categorized into 2 different kinds. The first one is countably infinite. A set is countably infinite if its element can be put together into a one-to-one correspondence with the natural numbers. In simpler terms, this means you can count the elements of the set even if it takes forever. For instance, set of natural numbers, integers, rational numbers, uncountably infinite. A set is uncountably infinite if its element can be put into a one-to-one correspondence with the real numbers. Let's see how can we find the cardinality of union of 2 sets given both the sets are finite. So let A and B be 2 sets, 2 finite sets such that A and B are disjoint. Then cardinality of A union B is equals to cardinality of A plus cardinality of B. The proof of this is very easy to follow using Venn diagram. So let's say that A is a set and B is a set and both these sets are disjoint. That means they do not have any element in common. Now, cardinality of A union B. A union B contains all the elements that are in A as well as in B. So number of elements in A union B would be number of elements in A plus number of elements in B. Okay, but now what if A and B are not disjoint? Let's say A and B are 2 finite sets and they are not disjoint, which means they have some elements in common. The intersection between A and B is not empty. Then cardinality of A union B is equals to cardinality of A plus cardinality of B minus cardinality of A intersection B. Let's have a look at its Venn diagram first. So we have a set A, we have a set B. A and B are not disjoint, therefore this gray shaded region represents the region A intersection B. And now A union B, cardinality of A union B is cardinality of this full set A plus cardinality of this full set B minus cardinality of A intersection B. Let's have a look at the proof of this theorem. Okay, let's consider the set A first. A can be written as A minus B union A intersection B. Let's have a look at the Venn diagram and see how can we write A as the union of these 2 sets. Let's have a look at the set A, which is the first circle. If you look carefully, A basically contains 2 regions, this gray region and the white region, which is not the part of B. So this region A contains gray shaded region and this white region. This gray shaded region, the elements here are the elements that belongs to both A and set B. So A can be written as the union of this gray shaded region and this white region. Now this white region contains all the elements that are the elements of A, but not the element of B. And A minus B, A difference between A and B, represents all the elements of X that are in A and not in the set B. So this region A can be written as the union of A minus B, which is this white region, union this gray shaded region, which is A intersection B. So A can be written as the union of the set A minus B union A intersection B. And if you carefully notice, you will realize that this white region, which is A minus B, and this shaded region, this gray shaded region, which represents A intersection B, does not have any element in common. And we just now showed that if two sets are disjoint, then union of those two sets, then the cardinality of union of those two sets is equals to cardinality of the first set plus cardinality of the second set. So cardinality of A will be equals to cardinality of A minus B, which is the cardinality of the first set, plus cardinality of the second set, which is cardinality of A intersection B. Let's have a look at set B now. If we go back and look at the Venn diagram again, then B again consists of two regions, this gray shaded region and the white region. This gray shaded region consists of the elements that are both in the set A and the set B. That means the shaded region represents the area B intersection A. It consists of all the elements that are both in A as well as B. Whereas if we look at this white region in the set B, it represents all the elements in the set B that are not in the set A. Basically, this white region inside B represent B minus A. And thus, we can write the set B as the union of this gray shaded region and this unshaded white region, which is A intersection B union B minus A. Therefore, B is equals to B minus A union B intersection A. Since it is commutative, intersection is commutative, we can write B intersection A as A intersection B. So therefore, we have B is equals to B minus A union A intersection B. Now, again, both the white region and unshaded region and gray shaded region are disjoint. And we know the property, if two sets are disjoint, then the cardinality of union of those two sets is equals to addition of the cardinality of those two sets. Therefore, set B, which is equals to B minus A union A intersection B, and both these sets are disjoint, and cardinality of B becomes cardinality of B minus A plus cardinality of A intersection B. Okay, so we know what is cardinality of A, we know what is cardinality of B. Let's have a look at the set A union B. So A union B basically consists all the points that are in A as well as in B. If we look at A union B, basically it contains both the circle. Now, if you look at A union B, it consists of this white region inside set A, this shaded region which consists of elements in both A as well as B, and this white region which is the part of the set B. Therefore, A union B can actually be written as A minus B union A intersection B union B minus A. And thus, we can write A union B as A minus B, which is the white unshaded region inside the set A, union B minus A, which represents the white unshaded region inside the set B. And then we have A intersection B, which represents the elements which belong to both A and B. That is the gray shaded region. Let's go back and quickly have a look at the Venn diagram once again. So we have that A union B is equals to this white unshaded region, this gray shaded region, and this white unshaded region. Okay, and if we carefully notice, this A minus B, which is the white region inside A, is disjoint with this gray shaded region, which is A intersection B, and both the sets are further disjoint with B minus A, which is this white region inside the set B. Therefore, A minus B, B minus A, and set A intersection B all are disjoint. This white region inside A, this gray shaded region, and this white region inside B, all the three sets are disjoint. And we know the property when the sets are disjoint, cardinality of their union is equals to addition of the cardinality of the individual sets. Therefore, A union B, which is A minus B union B minus A union A intersection B, all these three sets are disjoint. Cardinality of A union B will be equals to cardinality of A minus B plus cardinality of B minus A plus cardinality of A intersection B, because all these three sets are disjoint. Now, if we look at the original formula, we need to prove that A union B is equals to cardinality of A union B is equals to cardinality of A plus cardinality of B minus cardinality of A intersection B. Okay, but what do we have so far in our formula? We have that cardinality of A union B is equals to cardinality of A minus B plus cardinality of B minus A plus cardinality of A intersection B. So let's see what is the value of cardinality of A minus B. If we go back to this equation which is cardinality of A is equals to cardinality of A minus B plus cardinality of A intersection B, from this equation we have that cardinality of A minus B is equals to cardinality of A minus cardinality of A intersection B. So we can write the value of cardinality of A minus B over here is equals to cardinality of A minus cardinality of A intersection B. Cardinality of B minus A. If we go back and look at this equation, which is cardinality of B is equals to cardinality of B minus A plus cardinality of A intersection B, from here we will have that cardinality of B minus A is equals to cardinality of B minus cardinality of A intersection B. If we put the value of cardinality of A minus B and cardinality of B minus A from these two equations to this equation, we will have that cardinality of A union B is equals to cardinality of A minus cardinality of A intersection B, which we get from the first equation, that is cardinality of A is equals to cardinality of A minus B plus cardinality of A intersection B. And then we have n plus b minus n A intersection B, which we get from second equation, which is cardinality of B is equals to cardinality of B minus A plus cardinality of A intersection B. And then we have cardinality of A intersection B from the above equation. Okay. We can cancel out cardinality of A intersection B with cardinality of A intersection B. After cancelling out, we have that cardinality of A union B is equals to cardinality of A plus cardinality of B minus cardinality of A intersection B. This proves our theorem that two finite sets that have some elements in common, then cardinality of union of those two sets is equals to cardinality, sum of their cardinalities minus cardinality of intersection between those two sets. Now, if we have more than two sets, then we can prove that cardinality of union of those three sets will be equals to cardinality of the first set plus cardinality of the second set plus cardinality of the third set minus cardinality of the intersection between first two set minus cardinality of the intersection between first and third minus cardinality between second and third plus cardinality between cardinality of intersection of all these three sets. Now remember, whenever we are finding cardinality of union of these sets, we always assume that these sets are finite. Otherwise, the cardinality would just be infinite. Okay, so here when we are trying to find cardinality of union of A, B, and C, the assumption is that A, B, C all are non-disjoint finite sets. So go ahead and try and see if you can prove this property. If not, it's completely fine. In one of the videos, I will show you how to prove cardinality of A union B union C is equals to this. Now, whatever we have done so far is enough to start with probability theory. So from the next video onwards, we will get back to our series of probability. Goodbye.